Hello, everybody. This is going to be the lecture for section 3.4, derivatives as rates of change. So in section 3.1 and 3.2, we learned how to define a derivative, learned sort of like the theory behind it, how to construct it, learned the formula for it. Section 3.3, we've found some rules and some shortcuts to sort of quicken the process. So now we should be able to take derivatives much faster. Section 3.4, we're going to go ahead and delve a little bit farther into the idea of a derivative as a rate of change. So if you remember from section 3.1 and 3.2 and 3.3, the derivative, right, is the instantaneous rate of change at a specific point, right? Or the slope of the tangent line at a specific point, right? So for section 3.4, we're going to actually start sticking some natural and social science scenarios to this, so we can use at least some of the basics that we have to see how that how this is going to be used in sort of like the physical world. Okay, and right off the bat, the very first thing you can do with this is a bunch of physics. Okay, let me make sure I'm sharing my right screen. Awesome. Okay. All right. So just for quick practice, I'm going to go ahead and do one of these problems that I made you guys do maybe about a couple days ago. Just find the equation of the tangent line to a function at a value x equal 3. Use the graphing utility to verify your answer. So if you have your phone available, or if you have a second screen available, go ahead and scan the QR code. It'll pop up. The derivative calculator for the equation of a tangent line for you. I do expect all of you to be able to do the work. The calculator from the QR code is just to verify your answer, okay? So let's go ahead and jump into this one. So find the equation line, find the equation of the tangent line to f of x at x equal 3. So we get to go through the exact same process we are looking for. This is always going to be what we're looking for these, right? We're going to be looking for y equals mx plus b. This gives us the work already. That's going to be part 1, and this is going to be part 2. Okay, so part 1 is always going to be find m, right? Which means we need to take f prime of x. That's always going to be the very first step for one of these, right? So we need to find this equation of the tangent line. So the derivative here is going to be 2x plus 3. Okay, and we need it at a point x equals 3. So we need f prime of 3, which is going to be 2, 3 plus 3. That's going to be 6, 7, 8, 9. And that's going to be our m. So notice how quick this is now, right? So part 2, right, we need to find b. In order to find b, we need an extra point. We need another point. So we're going to go ahead and plug that value x equals 3 into our equation to get the y value of this, right? So f of 3, regular f, right, is going to be 3 squared plus 3 times 3 plus 1, 9 plus 9 plus 1, 18 plus 1 is 19. So the point that we're going to be playing around with, right, is going to be the point 3, comma 19. Okay, so let's go with that. So we know that our equation of our tangent line is going to be, right, y is equal to 9m plus b through our point 3, comma 19. So we're off to the races. Sorry, 3x plus b. So my y, 19, is equal to 9 times r3 plus b. 19 is equal to 9 times 3, that's 27 plus b. This tells us b is equal to negative 8. So we have our two things already. Our m, it gets us that thing, right? And our b up here. So my final answer, y is equal to 9x minus 8, and we are done. So notice how quick this is now, instead of having to use the limit definition, okay? So Next thing that comes up here is the quick checks. So just keep in mind, remember, okay, you only have to do the problems, the quick checks that are assigned to your discussion group. So if you are in group 2, you only have to do this one right here. Well, you only have to do the ones that have a 2 in them right here, okay? If you're in group 3, you guys get to do that one, okay? You have to do all the group, quick checks, but only the one with the 3, okay? Like you guys have been seeing, I've been grabbing answers from everybody from the groups and throwing those in our notes. So once I get through everybody's discussions, we'll have complete notes for the entire section. So if you guys need to practice, this is work that everybody else has done as well. So you can verify your answers that way as well, okay? So let's go ahead and move on. Let's go ahead and do some application of the derivative, okay? So remember how I was describing the derivative in section 3.1. It is the instantaneous rate of change at any value x equal a. That is the interpretation of a derivative, right? Now we get to stick that interpretation in various applications. So the first one we're going to do is for any of you that are going to be taking first semester physics. So I believe at LMC, that's physics 40. Okay, one of the very first things that you're probably going to learn is this thing right here, that suppose you had a position function, s of t, where s is a position in form of a distance, and t is given in the units of time, seconds, minutes, hours, whatever it may be, okay? Then the first derivative is the velocity, okay? And the second derivative is its acceleration, okay? This is what primarily makes up the very first semester of physics. You guys learn kinematics, that's what it's called, okay? So as an example, let's go ahead and do this first example that's right here, the only example of this section. A particle is moving according to the laws of motion, that equation right there, along a straight line where t is measured in seconds and s of t is measured in feet, okay? First thing I'm asking you here, find the velocity function, okay? And velocity function, right, that is just s prime of t. So long as we take the derivative of this thing, we have our velocity, okay? So s prime of t, super simple, 3t squared minus 8 times 2, that's 16, t plus 24, and we are done. That's what v of t is equal to, okay? What is the velocity after 1 second? Even easier. We get to find v of 1 second, right? So we get to use this equation. So it's going to be 3, 1 squared minus 16, 1 plus 24. 3 minus 16 plus 24. Minus 13 plus 24, I believe that is 11. Okay. So what we just found here, right, is at t is equal to 1 second, right, the particle is moving at 11 feet per second. So if you remember from the description of the problem, right, s of t is described in feet and t is described in seconds. So that means our velocity is in feet per second. Okay. The next question, when is the particle at rest? Okay, at rest means it's not moving. It's just not moving, okay? So that means we are looking for v of t, right? Or s prime of t, because we know both of those are equal. We're looking at when it's at rest. It's not moving, AKA the velocity is 0. Okay? So again, we get to use the equation for part A, right? We need to find out when 3t squared minus 16t plus 24, we need to find out when that is equal to 0. Okay? So if you take a look, let me clean that up a little bit, make it an actual plus 24. Okay, equals 0. So if you look at it, you can't factor out anything, right? And it's kind of difficult to do a, if you guys remember the diamond method, to do the reverse foiling, it's kind of, you can't do it sort of really off the top of your head here, okay? What always works when you want to find a quadratic equal to 0 is the quadratic formula. So the t, right, where the velocity is equal to 0 is going to be at minus b plus or minus the square root of b squared minus, let me give myself a little more, 4ac all over 2a, okay? And all that's left to do is call this my a, b, c, and we're off to the races. So minus a minus 16. Make sure that you're carrying the negative with a negative, okay? Plus or minus the square root of b squared, so minus 16 squared minus 4. Give myself some room again. A is 3, c is 24. Close that up. All over 2 times 3. Okay, so this is going to be 16 plus or minus the square root of 256, okay, minus 288 all over 6. 16 plus or minus the square root of negative 32 all over 6. So if you guys take a look, the answer that we got, this right here, okay, in particular, this right here, the negative 32 in a square root, tells us, right, that this is not a real number. Okay, since this is not a real number, right, we do not have, let me put this here, there are no t values where our velocity is equal to 0. So what does that mean in our problem? Our particle is never at rest. Does that make sense? Hopefully. Since there are no points, since there's no time t, okay, where the velocity is equal to 0, our particle is always moving. It doesn't ever stop, okay? All right, moving on. Where is the particle moving in the positive direction? So in this case, I'm going to want you guys to graph it. So I'm going to do by Desmos. Okay. So to find out when it's moving in the positive direction, right? That's when v of t, right? We know that this is s prime of t. If it's positive, then it is moving in the positive direction. So if the velocity is greater than 0, it's moving in the positive direction. Okay, and likewise, v of t being s prime of t, if this is ever less than 0, right, it's moving negatively. So this is, so if it's moving positive, it's moving forward. And if it's moving negatively, it's moving backward. Okay, so that means I get to go to Desmos. Let's go ahead, go to Desmos and drag this over. Okay, here's our velocity. Make it a little bit more contrast. There we go. So here is our velocity function. Okay, notice that our entire velocity function is above the x-axis. Okay, if it were to drop below the x-axis, then you have velocities that would be negative. It's moving in the negative direction. Okay, or it's moving backwards. But since all of the velocities are above the x-axis, means all our velocities are positive. So, and therefore, it's always moving forward. Okay, so. Okay, let me highlight my answers here. Okay, this one is the answer for this one. Okay. So, next thing, find the acceleration function. So from up above, okay, acceleration is the derivative of the velocity, right? Or the second derivative of the position. Okay. Thankfully, we have the velocity already. Our velocity function is given by the part A. Let me go ahead and scroll up. 3t minus 16t plus 24. 3t minus 16t plus 24. Okay, that is our velocity function. Okay. So then v prime of t, we take the derivative of this, it's going to be 6t minus 16. And we are done. This is our acceleration function. You see how quick this is now that we know the shortcuts? Okay. Last, find when the particle is speeding up and when it is slowing down. Okay. So you can do this by graphing as well, but I'm going to go ahead and show you guys the sort of the algebraic way of doing it. Okay. So we know what the acceleration function is. Okay. And just how we did part D, right? If it's speeding up, that means the velocity is bigger than 0. If it's slowing down, if it's moving in the positive direction, the velocity is bigger than 0. If it's moving in the negative direction, the velocity is less than 0. The same thing is happening with the acceleration. Okay, so when A of t is bigger than 0, right? Then this means particle is speeding up. Okay, and then when A of t is less than 0, then the particle is slowing down. It's decelerating. Okay. So how do we find this point? We know what the velocity, the acceleration is. Let's go ahead and find first when A of t is equal to 0. So then that means we need to find when 6t minus 16 is equal to 0. This tells us that t has to be 16 over 6. And if we reduce this a little bit more, it's going to be 8 over 3. And that is equivalent to 2.66 repeating seconds. So we know when the acceleration is 0. So when the acceleration is 0, that means it's not either speeding up or slowing down. But it hasn't answered our question yet. When is it speeding up and when is it slowing down? We found an important point, 2.6 seconds, right? Where it's not doing anything. It's not speeding up or slowing down. So what happens on either side of it. Okay, so I'm going to go ahead and do this again by Desmos. Okay, we know what the special point is. That's the 2.6. We're going to go ahead and go to Desmos again. I'm going to stick in our equation, 6t minus 16. So there's our point where we figured out that it's not speeding up, slowing down. So we know that everything after that point, the acceleration is positive. Okay, and everything before that point, the acceleration is negative. So it's exactly how you think it is. Everything after 2.66, the particle is accelerating. Okay, and everything before 2.66, the particle is decelerating. It's getting slower. Okay, so I'm going to go ahead and answer that here. So after t equal 2.66 seconds, right, the particle is speeding up. Right, and then after 2.66 seconds, after, so before, sorry, before 2.66 seconds, okay, the particle is slowing down. Okay, so let me highlight this really quick to show us that that's our answer. There we go. So this is sort of like essentially the basis of first semester physics. This is what we're doing here, okay? And it's just applying our calculus to the scenario that we have, okay? I believe in the lecture questions, I actually make you guys construct a kinematic equation, which is something that you would do for sure in a first semester physics class, okay? That comes up in our lecture questions, which is the very next thing down here. So that concludes the lecture for section 3.4. If there are any questions, please email me, shout at me through the discussion, come to my drop-in hours, anything you got to do, okay? Besides that, I'll see you guys around, and good luck on the problems.